Hi, my name is Natalie Walker, and this is my abstract submission video for TACSM.
Muscle pronation angle is a key characteristic in muscle function. However, current methodologies are tedious, time-consuming, and usually only include a few representative fascicles for pronation angle measures. However, leveraging imaging processing methods could improve the efficacy of pronation angle measurements while still providing valuable insights into architectural changes during specific tasks. To test this theory, we created an experiment where
Our purpose was to compare the manual versus semi-automated analyses for muscle pronation angle within the vastus lateralis using ultrasound images which were taken during isometric knee extensions at different relative intensities and relative to maximal volitional effort. So we used the ultrasound to take images of the vastus lateralis as seen here, and then these images right on the left, we have a resting image, and on the right, we have a contracted image where you can see that the pronation angle changes drastically based on what kind of contraction the patient is performing. So what we did was we used Image J and a MATLAB forum for our manual and our semi-automated methods to measure the different pronation angles. So with the probe, we collected these images. It's the same subject, same intensity. So for our Image J, this is a one at a time manual detection, which can be very tedious. So we average out 3 fascicles that we use for our overall pronation angle of that muscle. And so you can see here's the little toolbar for Image J. So to do each pronation angle, we have to use this angular measurement tool to measure every angle, at least 3 of them, so we can average it out to see what we think the average pronation angle is. And then on the right here, we see our semi-automated, right? We use a MATLAB form, which detects multiple fascicles and it averages them for you, as well as it traces the aponeuroses and identifying the muscle area to better understand the thickness of the muscle and where the fascicles we're looking at are. So right, with 6 clicks, whomever is doing this data will identify the superficial and deep aponeuroses to give this a tracing. It automatically gives you an average pronation angle for that muscle at that intensity. So what happened was so as you can see on the graph, overall, there was a mean effective intensity, meaning that the intensity did matter and was significant overall during different pronation angles changed with the intensity. And then 1 being rest and 4 being MVC. Here we can see the graph as the intensity increases, the pronation angle changes. For the semi-automated, which is here in blue, we can see that the pronation angle was a little underestimated, at least compared to the manual. And then for our manual, our resting pronation angle differed due to our angular changes, which is why we can see that this resting image or resting pronation angle difference for our manual is a little different than all of the other data points. So to conclude, the semi-automated method underestimated pronation angle compared to the manual measures, perhaps due to the fact that the semi-automated measure did not account for any changes in the angle of the deep aponeuroses. Significant differences in pronation angle were noted at 100% MVCs and not at other intensities, which is consistent with previous findings in the vastus lateralis research. Architectural pronation angle changes of the vastus lateralis with increasing force production may indicate fascicle rotation or muscle bulging, and may be more noticeable at maximal voluntary contraction compared to submaximal contractions. Thank you.